Oh, of course, tip it straight. Touch it. There we go. How's that? Yep, that looks okay. Okay, calculate area under a curve by estimation and integration. So we're going right back to the basics of this. Okay. I want to know how much area is under this curve between x is 0 and x is 3. How do I do it? Okay, so smart way is to integrate it if you already know how to do it, right? We're going to go all the way back to basics first, right? Let's assume for a second we integrate it. How do we know if it's roughly right? How do you know if you're miles away? Not sure? You've just been doing it blindly.
You can like close.
Okay, so where's the triangle? Underneath the graph. Okay. So super roughly, what are you expecting as an answer? Super rough. 15-ish. Right? Why? Right. I go across here for 3. I go up there for 10. I'm a bit less than half on this side, but if I cut that way, I'll have a bit extra here, so I should land somewhere around 15. Right. If you've got the opportunity to do that, you should, right? Because that took all of what, 2 seconds to make that estimate, and then if you get an answer of 200 and something, then you go, well, chuck that. Okay, let's assume for a second we don't know how to do integration. We'll work to that. Okay, I want to get a reasonable estimate for this thing. The 15 is a good start. Can I improve on that?
Boxes.
Boxes, okay. When you say boxes, rectangles, right?
Yes.
Beautiful. Where are the rectangles?
Above and below the line.
Above and below the line. Okay. When you say above and below the line, what do you mean?
From the x-axis to the point.
Okay, to which point? You're not wrong.
The point we know.
The point.
A point.
Okay. Could you give me a specific coordinate so that I know where you're thinking?
1, 2.
1, 2. Okay, so I'm going to make a box to there. Is that what you're saying? Yep. Okay, cool. So is that box my estimate for this entire graph then?
No.
No, okay. Do you want to draw more boxes?
Yes.
Where would you like to draw the next?
The next point is a definite point, so 2, 5.
Okay. Something like that? Cool. And continue the trend. Beautiful. Okay. Now what?
We want to make boxes that go on below the line instead of above.
Okay, so you want to do another set of boxes. Okay. Just before we do that, let's figure out what these blue guys add up to. Yeah, we'll do it like that. Cool. Okay. What do the blue guys add up to? Well, how do we get the blue guys?
Well, it's area on the rectangle.
2 times 1 plus
2 times
5 times 1. Yep. 10 times 1.
So that's 2 plus 5. So 7. So it's 7.
Okay, so that's our first estimate. Okay, may well be. Right? We'll refine our process as we go. Cool. Is there another way of using a similar technique?
Yes. 0, 1.
Okay. Let's go and pick.
And then minus 3 right from
Okay, cool. So I've got 1 by 1 plus 2 by 1 plus 5 by 1, so I've got 1, 2, 5, yep, cool. So we get 8.
And then do the in between those two, maybe?
In between those two, okay. Okay, how do I go in between those two?
17 minus 8 plus 8.
17 minus 8
No,
plus 8?
sorry, 17 minus 8. Wait, no. What?
Okay.
Find the
Yeah,
that's what I meant.
Yes, that's what I meant.
17 minus 8 plus, all over 2.
So 17
Is that what you're
minus
saying?
8. So 17 minus 8 on 2,
Yeah.
and then plus 8. It works, trust me.
17 plus 8. It works.
17 minus 8.
Over 2 plus 8.
Yeah, that was.
I think it's equivalent, yeah.
17 minus 8.
Yeah, that's an unnecessarily complicated way of doing it, but yeah, you could do it that way. How about instead you just do that?
Does that work? 17 plus 8.
Okay, let's write your way. So that's what your way was, yeah?
Yeah.
Which is the same as 17 minus 8. That?
Yeah.
17 plus 8.
Yeah, okay.
Yeah? Okay. I understand what your geometric reasoning for that is though.
Yeah.
So there's
It was more like finding the difference and then halving the difference and then adding that back to the start.
the basic, right? Cool. Regardless of which method you use, what are you doing?
Finding in between.
Finding in between, specifically the
Median, is that the mean?
the mean, yeah.
Yeah, which is adding all the possibilities and then dividing it.
Right.
Dividing it by the number of possibilities.
Right. Add up everything, divide by 2.
Yeah.
Quick pass. Yeah. Cool. Geometrically, what is this representing?
Right.
The
Halfway between what?
it's like triangles. It's like triangles in between the points.
This is pretty much on the line from here on in. Super close.
So we're gonna get a pretty accurate one from this one.
Well, you tell me. What do you think would happen?
That is pretty damn close.
Okay. So what do we get? 12 and a half. So what we get?
There's no difference.
Cool. Out of curiosity, what were we expecting on our original estimate? 15, right? Did we think that was going to be too big, too small?
Too
We didn't
big.
know.
Too big.
Why did we know it was going to be too big?
Because there's a lot more overhang than the actual one.
Because we was going from 0 to 10.
We go, well, actually, not necessarily, but anyway. Cool, this cuts across there. What do we do? Oh, I don't want to use that colour. Alright, not too bad. Actually, I'll do a purple dotted line. We should just go through. Cool, alright. Cool. This bit's going to underestimate, this bit's going to overestimate. The overestimate is clearly a lot bigger. So we're expecting 15 should be significantly too big. We've ended up with 12.5.
That's pretty far.
Pretty bang on? Okay, is it going to be bigger or smaller than that?
Small.
Smaller. Why?
Because we still have more overhang than the line gives.
Right. This bit's too big, this bit's too big, this bit's too big. It's always too big. Right? So this is an upper limit. So what are we probably expecting a perfect answer to be very close to?
12.
Probably pretty close to 12. Okay. Beautiful. Well, let's talk about these methods for a second. And I'm going to make sure I get this right the right way. Yep. Okay. I've got this blue method and this pink method. Okay. These are unsurprisingly called rectangle methods a lot of the time. One of them is called left rectangle, one of them is called right rectangle. So I've got blue and pink. Take a second to think which one is blue, as in you've got left, right, and blue, pink, right? One of them's like they match. Which way around do they go? Think about it for 5 seconds.
Right.
Blue's the opposite.
Blue is right.
Okay? So,
Blue's right.
Blue's left, 100%.
for blue, hands up for left, hands up for right. It is right.
What? Why?
Last year it was backwards. And it pissed me off so much that I remember it.
Okay.
I don't remember. I never did this last week.
So, the way that
this thing, I was thinking that.
the way that you tell, the rectangle will touch it on this side. Right? So the point of interest for all the blues is on the right side of the rectangle. Yeah? Now, at the end of the day, it doesn't really matter that much because you're going to do one or the other, right? And for all that I remember, I don't think the exams ever say left rectangle or right rectangle. They always give a bit more information so that it's clear. But they will give you exam questions that relate to this estimating stuff, which is annoying. That's why we have to keep doing it. But it's just so that you fully understand the super basics of everything. Okay. Well, that's all well and good. where did all these numbers come from?
The areas of rectangles.
We'll just say right, rather than writing right rectangle method, we'll just write right. I'll write in blue. Cool. Sorry, so where do those numbers come from?
Some of the
The sum of the areas of what?
The total number.
Okay, so I agree that it's the sum of the rectangle of the areas. Where did we get these specific numbers from? From the function, partially, yep. So, if I wrote, what I'm trying to do is generalize this. Where did the 2 come from?
Oh, the point where the number.
Okay, so f of 1, where did the 1 come from?
1 unit across.
1 unit across.
X.
It's
What does that 1 represent?
One a displacement of the X.
Yeah, okay. In terms of the rectangle, what does it represent?
Oh, it's the base.
The base, the width. Yeah? Cool. I'm going to call that a horizontal distance, so I'm going to call that h. Cool. We said we're doing a sum. Great. Where's this come from?
F is
F of
F of 2
2.
plus times X.
Say h again. This guy.
30 F of 3.
Cool. All right. Is that the most efficient way of writing that?
No.
No. How else would I write it?
F
You take H out.
Okay, we can take h out as a common factor for a start. F of 1 plus f of 2 plus f of 3. Okay.
We just write F of n where n is like an integer or whatever that one is.
Okay, so now we're getting a bit better. We can say h multiplied by, I've got a sum. What's the fancy way of writing sum? Sigma. Cool. Okay, what am I sigmaing? What am I summing?
F n where n is. Does it need to be an integer?
Okay, so this is where we start to
Can't it just be F of n, technically.
kind of just be f of n.
F of n where X is an element of n.
You get that. You get that. Let's go back to this because that might help to clarify. With sigma, should there be things above and below it?
Oh, wait, yeah. Oh, yeah.
Okay. Do we usually look at the bottom or the top first? Bottom. Bottom. So you start at the bottom, all right? What does it say at the bottom?
Minimum.
0. Does it always say 0? Okay, so a minimum. Yeah, where to start? True. How do you usually write it? Oh, it can be x, but usually it's. Yeah. Cool?
Yeah.
Alright. So, this is our index. We're going to start at some number, keep adding until we get to some other number. Okay. What are we starting at?
Which one do you say 0?
Are we? We're in blue.
Oh. Yes.
1. We started at 1, right? We started already over here. Okay. So, let's start at 1. What do we go up until? 3. Okay. 3. Cool. So, if I count those, I get 1, 2, 3. Alright? I've got 3 rectangles. That matches. And I hope everyone can count 3. Great. Cool. Now, this F, do I need to write 1, 2, and 3 in here?
No.
No. What do I need to write?
N.
Just N for now. Okay, great. Well, that worked out quite nicely. Okay, great. Cool. Alright, let's figure out left. How did I get to the left side?
Well, it'll basically be the exact same except n will start at 0 and very low 2.
Okay, so we got f of 0 times h plus f of 1 times h plus dot, 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 h So it looks like we've got that.
Wow.
We're okay with that? Yep. Okay. Where did this 1 and 3 come from out of this problem? Okay, now let's generalize this a little bit. We're going to call this A, or call that B. Where did 1 and 3 come from? Yeah, okay, but there's no 1 in there. Okay, so. Plus 1 to B, okay. Cool, okay. So that's what we've got so far. Are we okay with that?
Yeah.
Alright. Okay, so that works for this.
And the other one is
Why was this distance 1?
because it's starting with 0.
Right, I just chose that arbitrarily. Could I have had half? Does this work if I pick half? No. We need to modify this so that we can have arbitrarily small selections. So,
Does it not work if you have half?
okay, let's say I have half.
Yeah.
Oh, okay, yeah, because it's half. Oh, okay. 0 plus 1. So I've started it. Now I've got to think what I'm actually doing. Yeah, straight away we fail because we pick half. Then we'd have a thing in here which should be a half multiplied by 1 and a bit. Yeah? But if I put in half into this, I'm already starting at 1.5. So I'm already over here. Yeah? So this definitely breaks. Yeah? Is that okay?
Yeah.
Yep, okay.
What if you put negative on it?
For what? What's negative half? Okay. Okay, so we need to modify this. Does our start and end break? Does our end break? No? Okay. So the end doesn't break, does the start break?
Yeah.
Yes. Where do we actually want to start?
The first
The first known point.
The first point where both numbers are
The first time we were taking
Okay, how can I write that in the general form? So we've got A plus H, there you go. Right? So I start wherever I'm going and I've automatically got to move across a bit, H. Cool. Does that now work? Yes, I think it does. Beautiful. Cool. Now, slight little, only, yeah, no, that's okay. Yeah, that's okay. Other notation that you might see, we'll just switch these a little bit. And that H can be inside or outside, doesn't matter, because it doesn't vary. This could be I equals H. So that's a more common notation, but if I throw in the variables, it usually doesn't help us to generate it. But it means the exact same thing. Are we okay with that? Yeah. Cool. All right. Let's see if we can generate from this. Can we generate one for this? I need to check. Ooh. Any takers?
H sigma B minus H n equals
H, sigma. What do we do?
so B minus H on the top.
Yep.
And then the bottom is n equals A.
Go.
And then F is F of n.
Like that.
Yeah.
Does that work? We're starting it all now. Yes. think that works. Just shifting the count across. Yes. 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 That works. Cool. Beautiful. Now, why would I bother to show the fancy thing if you can just think of it like this?
But the fancy thing might be useful.
Why would it be useful?
Integers.
Not to do with integers. Integers, if anything, like this.
If the test is easier for a general solution.
Right, if it's on the exam, you need to be able to read and write it. So usually it'll just be multiple choice. Right, and it'll just have something, it'll be like, cool, here's the estimate we want you to do. Which one of these is an adequate expression for it? And they'll look rather similar, and then you have to be able to read and write that it starts and stops where it should, that the interval is the right amount, those sorts of things. Is this particularly difficult? No, right, you're literally counting rectangles, right, it couldn't be easier. Is it easy to stuff up with some of the placement of the indices and stuff?
Yeah.
Yes, right. That's fine. Beautiful. I think that's all I need to do with that. Double check. Yeah, that's fine. Yep. Cool. All right. Beautiful. Now, if you were asked what is the area under that curve, what would you actually do? You would actually integrate, right? Cool. Yeah, use the same thing. Beautiful. Okay. Black, blue, what am I going to do?
Actually,
Yeah, we'll do it. Okay, so there's a question, right? Beautiful. How do I actually turn this into pure math? Right, integrated, right? What's my fancy symbols?
big long S.
Big long S. So remember what that sounds like? What that? Summa. There you go.
Sumo.
Summa. S-U-M-M-A. Summa.
Is it still brick lettering?
No, that one I think is not Babylonian. What is it? Yeah, look it up.
One in doubt.
Alex has been talking about more complicated methods. Alex.
No, it's fine.
This one? What? I didn't put it there. Why you not
Yeah, it's just like, that's alright. No worries. Cool. Anyway, that's about. Cool. So I've got integrate, so summa.
Between 0 and 3.
Between 0 and 3. So we can say between 0 and 3.
0 at the bottom and 3 at the top.
Okay, so here, 3 there. Yep.
And then next to +1 dx.
+1. dx, beautiful. Didn't forget the dx, fantastic. Chief Examiner Mary Pat hates it if you forget the dx. Put the bloody dx on.
Why?
Because this doesn't make any sense mathematically, technically. Right? Well, we think
What does
we
that
know.
actually read as without the dx?
It's like if I just wrote like star 7, 3, I don't know, to the power of
I don't get, why does
X,
the
Y,
X
Z.
make it not make sense though?
Yeah, it's like most basically.
Does that make sense?
Ah, you're missing a bracket.
Right.
What was it?
This is an operation pair, just like that's an operation pair.
Why is it just a little symbol? What is the dx?
Now, having said that, do I always drop my own DX off whenever I'm doing my working? Yeah, all the time. Right, but if you're on an exam, put the bloody DX in. Right, it's an easy way to lose mark unnecessarily. The other reason, so if you've got this. Okay, I'll do that. What does that mean?
Circle.
What's a circle? What's a
Oh.
circle?
X squared plus y squared.
Is it?
I don't know, I can't see
The
it.
relation.
Wait, there's actually
And also you can't actually like put the DX because it doesn't make sense.
Okay.
Because it's not-
You could do that, but you could also do that.
Yeah.
And you can even do that. Right? So this has meaning later on. Right? So it definitely matters if you have your dx and dy's on. However, if the only variable in there is x, it's very, 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 very heavily implied that you're integrating with respect to x. But we don't really care about that. So all I'm going to say, whenever you do your integration, I highly recommend practicing putting the dx on. For other reasons as well, later on you'll have an integral like this, and then you'll want to do something afterwards. And if you don't have the dx on, you're going to end up integrating the entire line. Or you'll do something even worse. So, say what you meant to write was whatever, some number, something, doesn't matter what it is. 4 or something. Say you meant to write that and you didn't put the dx on. Very commonly, and usually there's more stuff going on, which is why people forget what they meant. Very commonly people will read it as they'll read it as that. If you don't have these dx's, do they look the same? Yeah, they look the exact same if you remove those dx's. Are they the same thing? No. Right, because this one's saying integrate 4, so you get 4x. This one's saying, no, just add 4 to the result. So they're out by a factor of 4x versus 4. Cool? So the positioning of the dx makes a difference. But if all you're going to do is integrate the whole thing, yes, I'm lazy and I'll leave off that dx very commonly. I highly recommend that you don't leave it off in your practice, purely because if you practice that way, odds are good under pressure, you'll do it that way. Right? So practice with the dx's on there. Anyway. Beautiful. All right, carrying on. What do we do now? Equals?
Is it the integral with 3 something minus the integral with 0 something? SS.
Say that again.
So integrate that something 3 minus the integral of that something.
Okay, is there a way of writing that?
1 over 3x cubed plus x.
Okay, so 1 over 3x cubed plus x, yep.
Equal line.
Line.
3, 0.
Beautiful. Cool. Now, here's my question. Am I putting the 0 to 3 on the x? Or am I putting the 0 to 3 on this x cubed and the x? Both, right? If I've got this line here, what is it telling me to do? Just that. So, I highly recommend use square brackets. Right? Because then you've got, obviously if you've got round brackets, they'll turn up all the time. Square brackets are rare enough that by doing it like that, you'll always recognize, okay, I've integrated this entire chunk, I need to put all of this in. Okay? Now we're just going through the motions. Oh, actually, sorry. You're telling me. What do I do from here?
Sum in 3 minus the sum of 0.
Beautiful. Cool. You'll notice I kept the square brackets. I highly recommend you do that Because as soon as you don't include those square brackets, people start to forget that, oh, hang on, I should be minusing both of these, not just the first one. Now, you don't have to take my advice. You are welcome to stuff things up and wreck yourself, basically. But from much experience of not just doing these things, but marking these things and seeing what very common errors are, put the bloody thing in brackets. It just saves you thinking when you're already stressed and underestimated. Cool. So we get whole thing equals 12. Yeah. Yeah. Again, here's a side note. Commonly, if I had to do this, right, I would have written the whole thing like that. And then this will just save me board space. Commonly, I'll do that. Take a guess at what that means. Right, if I put zeros into this, what do I get? 0. So if I do that, it just means if I put 0 in, I'm going to get a 0 result. So I really only need to put in the top bit. Cool. You are welcome to do that if you want. However, I will warn you, sometimes it will look like it should be 0 and it's not. So if you have, say, like e to the ax or something like that, and you've got 0 to 2, right? If I sub 0 into this, what do I get? 1, not 0. So I warn you, if you are going to play fast and loose with it, I'm not sitting the exam. Right? You're sitting the exam, so it's up to you. Anyway, but I'll probably be doing that on the board, just purely to save me writing da-da-da-da-da, oh, it's all 0. Cool. Not so much today, but later on when we do things. So that's good, beautiful, excellent. Do we think that's